So today I'm going to present a case study concerning the barrel aging applications in Chardonnay and Sauvignon. So why barrel aging is important for these varieties? It's important because this wine needs to be aged, but they don't age the same way. So we all know, and this is the proof, Chardonnay and Sauvignon, they are completely two different wines. They have different composition. And this is the heat map of the global composition of a Chardonnay Sauvignon blend matrix, which is completely an example. So we use oak to maturate them, and oak, it's a very important moment for the wine because it has to be a very successful marriage. The oak is going to give extractable compounds that are related to the raw material, the wood, and only 5% of this, the wood composition concerns the extractable compounds. The non-extractable compounds are essentially ellagitannins and some aromatics like lactones and whisky-lactone in particularly. On the other hand, we have 95% of non-extractable compounds, especially macromolecules like lignin, cellulose, hemicellulose. And toasting is an important factor during cooperage because toasting is going to degrade the macromolecules and form volatile compounds that are very important for the winemaker. So we age the wines in barrels, and of course we follow them for many years, until now 4 years after bottling. So I'm going to present some main results concerning the composition of the oak that we use and the impact of this composition to wine's oxidative stability after many years on the bottle. So we started working in the composition of the oak because for a physical chemist it's important to know what material it has on his hand in order to better understand this very complex phenomena. So we work with a copper who used to characterize the staves based on the tannin potential, and this characterization is based on essentially the known ellagitannins. And of course, we use different toasting levels. So we have low tannin potential, medium tannin potential, and high tannin potential wood staves that were in contact with the wines. So generally, when you extract the staves in an ellagittannic perspective, normally, as expected, the low tannin potential wood has less ellagitannins than the high potential wood. But the more interesting result is behind the composition of this ellagittannic content, because the tannin potential is related to the different ellagittannic composition. Indeed, we have bigger ellagitannins, granadine and roburin, correlated with high tannin potential. Instead, vascalagine and castelagine were essentially correlated with low tannin potential. And this is important not because the winemaker is going to follow the molecules, but because these different compounds have different reactivity during aging. So vascalagine and castelagine are more reactive than the bigger granadine and roburin. So when we target the ellagitannins and we try to discriminate the good extracts, I don't show the results, but the sum is that there is no clear discrimination of good tannin potential based on the ellagittannin content. That means that the 9 known ellagitannins are partial indicators of good chemical composition. If we run metabolomic approach, that means if we analyze the globality that we can get with our instrument, in our case more than 1,000 extractable compounds, then you get clear discrimination. That means that not only you have the 9 extractable known ellagitannins, but you have other compounds less considered, unknown, that are more effective than the ellagitannins. And this is really very important. We check also the toasting, and we can tell that the toasting level is very important because it modifies the profile, the chemical profile of the extractable compounds. And the toasting level can go from the very low potential, like BL with